Welcome to this explainer. Every time you flip a switch or turn the key in your car, there's this silent, perfectly balanced symphony of physics taking place behind the scenes. Today, we're doing a rapid refresher on the absolute foundational laws that make modern engineering possible. We're going to take those complex formulas and turn them into a totally intuitive visual journey. Let's get right into it. Think about it. Electricity literally powers our entire world, yet it's completely invisible. So how exactly do engineers calculate things like wire gauges or battery capacities when they can't even see the electrons? Well, we rely on a very strict set of fundamental rules that govern this hidden force. It's what allows us to predict and actually harness the whole shebang. All right, Section 1, the core of electricity. We're talking about Ohm's law. To really grasp Ohm's law, let's quickly review the triad, starting with voltage, or V. You can just think of this as electrical pressure. Just like the forceful push that gets water flowing through a pipe, without that potential difference, absolutely nothing moves. It's exactly why a 12-volt car battery delivers a much harder push than your standard everyday 1.5 volts AA. Next up is current, represented by I. If voltage is the push, well, current is the actual electrical charge in motion. Going right back to our plumbing analogy, it's the sheer volume of water rushing through those pipes. Measured in amps, this volume of moving charge is the crucial metric we look at when we're evaluating electrical safety. And finally, we have resistance, or R. This literally opposes the flow of charge. Imagine a sharp pinch or a kink in that water pipe just slowing everything down. Measured in ohms, it acts as a natural speed bump. In fact, engineers use specific components called resistors to intentionally restrict current, often bleeding off that extra energy as heat, just to protect our delicate electronics. So here's the real magic. These three elements are permanently locked in a perfectly proportional mathematical dance. V equals I times R. And because of this lockstep relationship, if you know any two of these values, boom, you instantly hold the key to finding the third. Moving on to Section 2, unpacking network circuits. We'll look at series and parallel. While Ohm's law is absolutely perfect in isolation, real-world applications are rarely that simple. If you crack open any device, you'll see this complex web of resistors, capacitors, and voltage sources. So to understand how electricity navigates this crazy maze, we need some systematic rules. And really, there are two fundamental ways to arrange these networks, series and parallel. In a series circuit, components are connected end to end. There's literally only one path, so the current stays exactly the same throughout, while the voltage divides. But in a parallel circuit, the components connect right across the same nodes. They're sharing the source, meaning the voltage holds steady, but the current actually splits off to take multiple different paths. Now, this creates a pretty fascinating dynamic when we calculate equivalent resistance. In series, every new component is basically just another hurdle on a single track, so you simply add them up. Easy, right? But parallel circuits are wonderfully counterintuitive. Because adding more branches gives the electricity more paths to flow through, adding components in parallel actually decreases the overall total resistance of the network. Wild, isn't it? Okay, Section 3, solving a real circuit. Let's do a quick example. Time to put you in the driver's seat. Imagine a circuit powered by a standard 12-volt battery. We connect that battery end to end with a 4-ohm resistor and a 2-ohm resistor. Because it's a single loop, we know right off the bat it's a series circuit. Our goal here? To calculate the exact current flowing out of that battery. Let's break this down into two simple steps. Step 1, we find the total equivalent resistance. It's a series circuit, so the rule is a piece of cake. Just add them up. 4 ohms plus 2 ohms gives us a total resistance of 6 ohms. Okay, step 2, we apply Ohm's law. We take our total pressure, that's our 12 volts, and we simply divide it by our total resistance of 6 ohms. And 12 divided by 6 equals exactly 2 amps of current. And remember the golden rule of this specific setup. Because there is only one single path, those 2 amps flow equally smoothly right through both of those resistors. Look at that. You've just mathematically mapped a real-world electrical network. As we wrap up this explainer, I want you to remember that literally every piece of modern technology, from a simple little flashlight to the massive power grids lighting up entire cities, relies on this delicate mathematical balance of voltage, current, and resistance. It's a universal law that's just hiding in plain sight all around us, which leaves me wondering, as you're processing all of this, what kind of complex network circuit is firing away inside the very device you're watching this on right now?